Hi, everyone. We'll get started in 1 minute as we let everyone trickle in, but thanks for joining. We're really excited for you all to see this lab visit. Okay, so we'll get started. We are so excited to have the first lab visit of the course. And we want to welcome David, who is a PhD student at Will Oliver's lab at MIT. It's the Engineering Quantum Systems Lab, where they work on superconducting qubits. So I won't take any more time, but I'm actually going to turn it over to David, who's going to tell you a little bit more about what they do in the lab, as well as show you around. And so you can actually get a real feel about what a quantum lab is like. So David, take it away.
All right, awesome. Thank you so much, Kiara. So again, yeah, right. I'm David. I'm a second-year PhD student here at MIT in the Engineering Quantum Systems group, where we study superconducting qubits. And I'll, be essentially explaining these words, and hopefully the takeaways from today will be, seeing sort of what a day in the life of a PhD student in this sort of field might look like, and sort of explaining maybe some of the basics around what we do, what samples we care about, and how we measure them, and the science that we get out of it. So I'll start with just saying something very low level, or maybe not so low level, but in any case, the problems we care about in this laboratory involve things that are kind of like atoms. Namely, atoms have protons, electrons, and neutrons. And by combining these things in certain ways, you get all of the elements. And so you'll have like a proton or some sort of nucleus in the middle and some sort of electron cloud surrounding it. And what that might constitute is an energy level structure that looks like this, where electrons like to sit with certain energies. And okay, great. So you could have atoms and you could probe them in physics laboratories, and that's more, for other fields. What we like to do is actually create artificial atoms in our laboratory. So what I mean by an artificial atom is, instead of protons, electrons, and neutrons, we're going to make circuits out of superconducting metal that are comprised of capacitors, inductors, and a fancy element that's sort of like an inductor called a Josephson junction. And from that, we actually get a very similar energy level structure to this. And so we call these things artificial atoms. And you might have heard the word qubit. The reason we call, what we're working with qubits is because we can actually just selectively play with the first two levels of them. Okay, so that's enough of the board. Now we'll go on to, actually showing you what the qubits look like, and then all the equipment and, apparatus we have to measure them. So I'll turn this around again. I just entered a part of the lab that we call the staging room. Namely, in any experimental physics lab, you're going to have a lot of equipment and a lot of tools, because you're going to need to solve a lot of problems when things break, and you're going to need to prepare your samples. So some things you might see are things like, drawers that are filled with samples, tool cabinets that are filled with tools, other things, a lot of computers to control and debug things. And what I'm going to do is show you this optical microscope that will show us, hopefully. Live demos are never a great idea, but let's see if we can get it to work. One of our superconducting qubit samples. All right, great. So there it is. What I'm going to do is zoom out first. Okay, so what I have in the picture here is a 5 by 5 millimeter little chip. It's called a chip that is made of a substrate of silicon and a bunch of evaporated metal on top of it. And there's a lot of scratches on this one. So this one's probably not going to be a very good qubit, but I'll just break it down for you. So what we have here is some, center thing going through the whole chip, and branching off of this center line, which we use to, measure and address our qubit, are all of these squiggly lines. And I'll zoom in to one of these constituents now. Alrighty. Great. So what's happening here is, we have components patterned onto this chip that behave a certain way, right? And this guy here, the two big metal pads form a capacitor. And that guy right in the middle, if I could zoom in close enough to show you, that is our, the other element called a Josephson junction, which, is the real magic sauce of these qubits, these superconducting qubits. So this guy right here is a superconducting qubit. That's the takeaway from this optical microscope. And to make them, you need a lot of fancy equipment, and fabrication. And in our lab specifically, we've partnered with a national laboratory at Lincoln Labs, and they, sort of help us create these samples. But the long story short is this is what our samples are, artificial atoms actually look like. And they're very small. Like I said, the whole chip is 5 millimeters by 5 millimeters. But if you zoom in, this whole square right here is around 100 microns. A micron is a millionth of a meter. And then if you, zoom all the way into this guy, things start getting into the nanometer scale, hundreds of nanometers, tens of nanometers. A nanometer is a billionth of a meter. Sorry, yeah, right, these prefixes, right. Okay, in any case, they're very small, so you cannot really see them with your eye. But, right, they comprise, they're much bigger than natural atoms. And the crazy thing about this is that you can realize quantum behavior on much larger scales than you would realize them with your natural atoms. That's the sort of magic of the things that we work with. Namely, we build these objects that are much larger than natural atoms, like I said, which are on the scales of like angstroms, 10 to the minus 10 meters. And with them, we realize the same sort of quantum behavior. And what that does is it gives us the opportunity to really precisely engineer systems that behave the ways we want to, for example, to process quantum information, run quantum algorithms, or do sensitive measurements with very fancy quantum mechanical protocols. This is a field called quantum sensing. So it's rather miraculous that we can do this, and that's why there's a lot of excitement in the field, and a lot of large tech companies, as I'm sure you know, are investing a lot into this. There's a lot of hype in the field, namely because there's been a lot of progress in the last few decades, and no one is really sure where the progress is going to stop. So everyone's just sort of running as fast as they can with making these devices better and better and exploring. So it's a very exciting time to be in this field, is what I'm saying. And it all starts with what I just showed you, that little evaporated piece of metal, which behaves like an atom in certain ways. So now what I'll show you is how we measure these guys. So I'm going to take you out of this room, and I'll sort of go through this as an office. As a grad student, a lot of your time is going to be spent designing circuits, in the initial stages of a project. Once you design the circuits, then you get to move on to the actual measurement and characterizing them. This machine is a very important machine in our lab. It provides coffee. That is a very important piece of apparatus. You do not want to have that broken. Limit productivity. Okay, so now we're in the hallway of the Materials Research Laboratory at MIT. And typical things you see in these laboratories are, canisters of gas and dewars filled with liquid nitrogen. And here is our laboratory that I will let us into. Fantastic. So it looks rather mysterious. There's these 4 big cans, and connecting to the cans via, these overhead lines, there's these 4 big racks of equipment. Now, I'll just explain to you, our qubit sits very low, deep inside one of these. They're actually just refrigerators. They're called dilution refrigerators because they get much, 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 much colder than any other kind of refrigerator. In fact, the temperatures reached at the inner, deeper stages of these refrigerators is the coldest place, or the coldest solid place in the universe. I would like to repeat that because it's pretty impressive. The coldest place in the universe. In outer space, you get thermal radiation that's around 1 Kelvin. At the deepest parts of these refrigerators, in order to explore the physics of our devices, we get to temperatures that are 1,000 times smaller than that, or 100 to 1,000 times smaller, namely millikelvin temperatures. So how do we do that? Well, it turns out that these overhead lines connecting these big racks control the gas and use fancy physics in order to promote the cooling power of these refrigerators. I won't get into details, but I'll just say these things are worth hundreds of thousands of dollars. So to get a lab started, it takes quite a lot of overhead. Thankfully, as I said, there's a lot of interest in these things. So and we have a bunch of them. And what I'll show you now that you know what they sort of look like, I'll take you inside of one, and I'll also show you how we control them. So now we are going to go upstairs.
So David had said that he might lose internet connection at some parts in the lab. So this is one of them. David, if you can hear us, just know that you're frozen right now. Oh,
Okay,
you're back.
how about, okay, great. I was just saying that the internet connection might freeze. So okay, perfect. Okay, so now I've taken us upstairs. This is another room directly above the room I just showed you.
David, just quickly, how many people are in your lab?
You could round it up to 30. There's around, I think, yeah, maybe like 15 to 20 PhD students and undergraduate researchers who get involved, and then maybe 5 postdocs. But because the field is doing very well and our lab is getting a lot of good results, we're hiring a lot and getting a lot of grants. So in this field, the groups are getting bigger and bigger. So yeah, it's on the larger side for experimental physics groups for sure. Yeah, so this is the room where we control all of the refrigerators that I showed you. Namely, you'll have computers that.
Oh, David, it's cut out again.
How about now?
Yep, you're back.
Okay, I've switched to data, so hopefully, the Wi-Fi won't be an issue. These curves just show how cold the refrigerators are and what the temperatures are. All of ours happen to be warm, and I'll just show these electronics also cost a lot of money, maybe tens to hundreds of dollars to actually address the qubits inside of the refrigerators. What we do is we have things like microwave sources. Microwaves are they're just signals in a certain frequency range, namely the gigahertz frequency range, so 10 to the 6 hertz times per second. And we have these sources. We have things called vector network analyzers that we plug into in order to see how the qubit responds to our pulses, and a whole host of other electronics in order to address them. Right. Okay, so you sort of see what our office looks like, so to speak, where we have these big fancy computers and these refrigerators. Now I'll take you inside of the refrigerator. We're walking down the hall now to another laboratory. Right. So I guess this would be a good time if there's any questions or anything that anyone's brought up.
Yeah, so why do the diluted refrigerators have a different look than really the golden chandeliers that we see from companies like IBM?
That's because those refrigerators are open, but inside of the refrigerators that I just showed you, they look like that. So I'll just that's perfect timing for this. I brought you into this other laboratory, which we have. Now you get to see, this is what a laboratory looks like when it's not so set up yet. So, I'm in the process of setting this up with some other graduate students. Things are just starting to get up and running, but, it's not as neat. So sorry for that. Now we're going to go into the other room. This is where all the computers and control electronics are. And then what we do is we route the cables through the wall. And through the wall here, I'll just take people with me for a little bit. Now they come through the wall, they go, up and down into the refrigerator. And then, these are where, the pulses and, the things that we use to control the qubits are coming from. And they go into the refrigerator. and then they slowly snake their way down. And these are the cables here in these fancy, bent shapes. And then they snake their way down and down. At this stage, they're at, no, here. At this stage, they're at 50 Kelvin, the temperature. As you go deeper, it gets colder. Then you get to the 3 to 4K stage. So 3 to 4 Kelvin at this stage. And then you get to a few hundred millikelvin, and then even colder. And you see the microwave cables are just snaking their way down. And then you get to the coldest stage. This stage houses something called the mixing chamber, where the real magic of the dilution refrigeration process happens, but that's irrelevant. This stage is at around 10 millikelvin, ideally. And then you break out your signal into all sorts of wires. And then what you'll have down here are these little packages that you route the signal cables to. Nothing's connected right now, but this would really look a lot more crowded if everything was connected for the experiment that I'll be conducting soon. So in any case, these packages, inside of them, if you open it up, it will have one of those 5 millimeter by 5 millimeter chips that I showed you on the optical microscope. So the story here is that you have something coming from room temperature at 300 Kelvin, right? 300, that's a large number, all the way down to 10 millikelvin. So that's orders and orders of magnitude smaller, right? So there's actually a lot of fanciness that you need to do in order to get your signals, from up there to down here and have them, be as you, need them to be, which is, very particularly shaped pulses and very particular frequencies. And, you want very clean waveforms in order to get the qubit to respond the way that you want it to, and, really address it in the quantum mechanical limits. And I'll just say the reason that you need such fancy refrigerators in order to operate these qubits is because of their energies. Namely, if you have, thermal energy in your system, like, we exist at 300 Kelvin, then it turns out if you have a qubit with a smaller energy, then you're going to get, the thermal energy kicking your qubit state around and exciting it when you don't want it to be excited. But if you have your qubit resting at 10 millikelvin for the frequencies that we use, then the qubit sits nicely in its ground state. So the thermal energy doesn't become a problem. So that's why you need this whole thing in the first place. And yeah, the real magic of the superconducting qubit community is the fact that it's so easy to engineer circuits, very complex circuits the way you want them to. But one of the problems that the field is running into is you could see how crowded these microwave lines are, and how how complex it could get to get all the lines down to your qubit to route your lines into these things are called packages where we put the qubits. So one of the challenges in the field right now is figuring out how to scale the refrigerators such that we could get to the higher and higher number of qubit regimes. Namely, these days we have like tens of qubits to hundreds in the near future, and then people want to eventually promise millions of qubits so you could start realizing very fancy computing that is fault tolerant and error protected and this sort of thing. So the field is, no one is sure where the progress is going to end, right? That's why it's a very exciting field to be in, and there's a lot of cool science that's gonna hopefully come out of the progress and effort that people are putting in these days. So I hope that was somewhat illuminating. I would just like to reiterate that it's a very exciting field to be in, and a day in the life of me as a graduate student might be composed of maybe spending a few hours debugging something here, maybe spending a few hours doing simulations in toolkits that other people made in Python, maybe spending a few hours thinking about how to best communicate my idea in a presentation. As a graduate student, you have to give a lot of talks and presentations to people because the more time you spend thinking about an idea, the more obvious it seems to you. But when you communicate the work through papers and presentations, a lot of effort has to be put into making your thoughts clear, because at the end of the day, communication is the final link between you and everybody else in your ideas. So that's a very, very crucial part. I can't emphasize that enough. So in any case, you sort of get to do a lot of different work as a graduate student. And it's a very beautiful thing because when you're in a PhD program, then you get to sort of explore ideas that you more or less want to explore. So you're given a lot of freedom. For example, for me, you come up with a project idea, you ask people about it, see if it's a good idea or not, and then you just get to realize it. And in a laboratory like this, this goes to all of physics essentially, there's really nothing separating you from nature at the end of the day. If you want to do something, you have all the tools and all the time you need, and hopefully the funding you need in order to just go out and see what you can do. So in a laboratory like this, we focus on the problem of these quantum circuits with our superconducting artificial atoms or qubits. But yeah, right. What I'm saying now is sort of broad to all sorts of PhD research. All right, are there any other questions? I think that's just about what I wanted to show you.
Yeah, David, this has been so cool. Just a few questions. One, why are what's behind you? Like, why are they typically gold? Is there a reason for that? Does it?
Absolutely. Yeah. Thanks for asking. So, in fact, a lot of the parts we have are plated in gold, because when you get to such low temperatures and work in these really exotic regimes where the thermal conductivity, namely, how heat transfers between, these metal pieces is so important. It turns out that if you have like a piece of copper or something by itself, copper likes to form an oxide on its surface. Namely, oxygen likes to sort of accumulate on the surface, and it forms a little layer above it, and this layer is a bad thermal conductor. So when you plate things with gold, this oxide doesn't form, and so you get very good thermal contact between components. So that's the magic of having everything plated in gold and look so shiny and nice. So it's not just to impress people with the looks, although it maybe it does that as well, which is not a bad thing.
And then what's the end outcome that your lab is trying to achieve?
That is a very, very good question. So I guess I'll address it in a sort of, it's a big question is what I'm saying. Namely, our lab has a lot of different research thrusts because we have so many people working on so many different things. I don't think there's any one unifying scientific question that we're all, well, okay. I think we're all very excited about learning how to engineer better quantum systems. Namely, when you create these sorts of circuits, put them in this environment and you want to probe the, either the quantum mechanics of these things, you run into problems on, how you can, let me rephrase. There's a lot of challenges that come into play when you're trying to make these artificial atoms and when you're trying to create them for specific purposes like quantum information processing. So everyone in our lab is dedicated to a whole host of problems generally belonging to that field. Right, so the outcome that we're excited about is building very good quantum hardware and exploring a lot of interesting physics that you can realize with these very precisely engineered quantum systems that you might not otherwise find in nature. For example, atoms in their natural form, protons, electrons, and neutrons, they form in specific ways, and chemistry sort of tells you how they like to interact. We can engineer systems that regular atoms do not like to form. And then we could probe the physics of these systems and hopefully explore, sort of lesser known and lesser probed areas of quantum mechanics to sort of, realize interesting behavior. I hope that sort of answers the question.
Yeah, that was awesome, David. Again, just wanna thank you so much for taking time out of your Sunday to give this lab visit. It was absolutely incredible. And I know we're getting a lot of comments from students how much they appreciated it. So just want to thank you again, David, for taking the time. This was super eye-opening. And with that said, for all the students that are on the call, it's 5 minutes until lecture starts. So you have the next 5 minutes to take a break, and then we'll be getting started with the lecture. So thanks again, David, and for showing us around and a lot of students were asking what's the lab what lab is this at MIT. So for everyone that just wants to be aware, this is William Oliver's lab. At MIT, it's the Engineering Quantum Systems Lab, where they focus on superconducting qubits, which we will focus more on what superconducting qubits are next semester as well. So get excited, students. You'll get to understand a little bit more about everything that David's talking about and working on.
All right, thank you so much again. Glad to have given some insight into this world, right?
Yeah. Thanks so much, David.